So I attach the mass and I pull it down to here, or it just naturally comes to here, and make sure that it's not moving at all. So it's static equilibrium. And this distance here, x1. Because it's an equilibrium, I know that the weight must equal the spring force there. So mg must equal k x1 minus x0. Because that's how far the spring stretched from equilibrium. I am now going to take this and I'm going to pull it down and let go. Not equilibrium.
Is that because it's gonna be moving immediately?
Yes, it's going to be accelerating immediately.
At what point would it decelerate? Is that something?
Well, acceleration is a generic term in physics to cover speeding up, slowing down, and changing direction. But it actually is going to start slowing down once it passes this point.
Okay.
And then it'll hit some peak up here, then it'll start speeding up and then slow down, and back and forth.
Which is why it's harmonic.
Yes. So that's this.
And is that gonna be x2?
Yes. So I have, if up is positive, I have k times x2 minus x1 equals mg. Nope, that is wrong. Minus mg equals mk. I want to make sure I'm not going to screw up the minus sign here. So x2 is just a distance. So if x0, x1, and x2 are distances, then this should work out. Because that's a positive number. Okay, I'm good with it. Questions up to here? Okay. You're just giving me the finger?
Yeah.
So let's expand on this right here.
So mg equals spring constant for x1.
Say it again?
Mg, or wait, equals spring constant or?
No, it's spring
elastic
constant
force?
times the displacement from equilibrium. So I have k x2 minus x1. Sorry, minus x0. I did do x0 there. Oh. That should be 0 there. Minus mg equals ma. Go ahead and distribute here. We get k x2 minus k x0 minus mg equals ma. I know from the second situation there, where it's an equilibrium with a mass on it, I know mg is equal to k x1 minus x0. So I have k x2 minus k x0 minus k x1 plus k x0 equals ma. Those cancel out. I'm left with k x2 minus x1 equals ma. People just catch up, ask questions before I talk about why this has any significance at all. Okay, let's talk about the significance then. x2 minus x1 is the distance from here to here. That's x2 minus x1. This equation that I end up with there is the same problem as if I put this thing horizontally with a mass already attached, and I stretch it out to some new quantity. So if that's x1 and that's x2, x1 minus x2, or sorry, x2 minus x1 is just the amplitude. It's how far I pull it out before I let go. So when I'm dealing with the vertical spring problems, I have two options. I can take weight into account. If I do, this is the equilibrium position right here, and I have to look at how far it's stretched like that. Or I can ignore weight and treat that as my equilibrium position, and how far do I stretch it from there? And the same goes true with energy. So if I'm looking at the potential energy and kinetic energy of a situation, if I consider this to be my equilibrium spot, then I have to bring in MGH into my equation. If I consider this to be my equilibrium and how far do I stretch it from here, I don't have to worry about gravitational potential energy. It's going to cancel out. Now, there's probably a 10-minute derivation to show that's true. I'm just going to have to accept that on faith. But it's a similar derivation to that, just more.
So x2 minus x1 is amplitude, you just said.
Say that again?
x2 minus x1 is amplitude.
Yes.
So k times amplitude equals ma.
If you consider this to be the equilibrium, then k minus that amplitude would be ma. If you do it, this is the equilibrium, and it stretches that far, then k times that amplitude minus the weight equals ma. Let's actually work through some math.
Okay.
Because a day without math is like a day without sunshine.
Yes. There's no sunshine. I was about to say the same thing.
So I have a spring, hangs 2 meters naturally. I add a 3 kilogram mass, and the spring is now 5 meters long. I then pull the spring .5 meters more. And let go. What equation models the movement of the spring? And I'm going to tack on ideal spring, because damped harmonic motion requires calculus. Actually, differential equations more specifically,
Oh joy.
which is beyond the scope.
Of this class, hopefully.
Yep.
Okay.
So the first bit is, let's draw out the picture here. I have a spring that naturally is hanging 2 meters long. I add a 3 kilogram mass to it, and the spring is now 5 meters long. 3 kilograms, and this is 5 meters. So the first bit is just so we can figure out what the spring constant is. Let's go ahead and put this on Earth 2.
No. I mean, yeah.
We don't have to.
No, it's okay.
So tell ratio to gravity, 10 meters per second squared. This is an equilibrium. And so I know that mg is equal to kx. 30 is equal to k times 3. K is 10 units.
10 what now equals K? Is that what you're asking?
Yeah.
Newton meters? No, I guess.
You'll have to work out.
Oh,
Is it mg
squared?
over x?
Newton meter squared?
No,
Mg over x?
Newton meter.
those aren't units, but those, what are the units of mg?
Oh, Newton meters per second squared? What?
You just guessed that.
I don't know.
Right? mg over, what are the units of this 30?
Meters
MG.
per second squared. Meters
MG.
squared per second squared?
mg, not units. Pardon? Oh,
Meters?
well, not in this context.
Is it not meters squared per second squared?
No.
What? G equals.
All right, what are the units of mass?
Kg?
Sorry.
What are the units of little g?
Meters per second.
Meters per kilogram meter per second squared is the same as, what are the units of this 3?
Which is x.
Meters, yeah, which is x. So that's meters, so this would be, that's 30 newtons, and that's 3 meters, so it's newtons per meter. Not newton meters. And there's no squaring there, unless you really,
Screw something
I
up.
guess it's a newton per, newton, no, it would be a kilogram per second squared.
No, that's right.
So the spring constant is 10 newtons per meter. I now take that spring and I stretch it down an additional 0.5 meters. Not the scale. And I let go.
Right.
I am going to assume this is like equilibrium right here, where it is with the mass. So I'm not going to worry about weight in my formulas now. I know that my mass is 3 kilograms. I know K is 10 newtons per meter. I know my amplitude is 0.5 meters. Well, from here, I can figure out other things. My angular frequency, I know is the square root of K over M. Making sure I got that in the right order. Let's see if that's good. Yeah, that works. So from that, I know my angular frequency is 10 over 3, square root of 10 over 3, which is 1.8.
8,
Let's go one more decimal point.
3.
Units?
Radians per second.
How did you get 30?
Here,
Yeah.
the mass was 3 kilograms.
Uh-huh.
Little g, I put it on Earth 2, so
Oh.
10 meters per second squared. So omega, I know it's gonna oscillate in harmonic motion. So its position, well, now I have to sort of define a coordinate system here. If I choose that to be 0, this to be positive 0.5 meters, and this would be, in that direction is negative. I have, I'll use y. Y equals my amplitude, 0.5 meters, times, why should I use cosine here? I heard sounds, but I did not hear words.
I was still writing stuff down. Can you repeat that?
Because it's starting.
Why should we use cosine?
It's starting at the trough.
Yeah, or starting at an extreme.
Yeah.
So 0.5 cosine, because cosine curves start at the extreme, sine starts at 0. Cosine of 1.83 radians per second times time. That's a t. And that is the equation that models the movement. If I chose it up to be positive instead of down, then, so this is up being, this is down being positive. If up were positive, then it's starting at the trough, that's at the lowest value, it'd be negative 0.5 meters cosine of 1.83 radians per second t. But wait, there's more. I didn't ask for, we actually answered the question, but let's go ahead and extend it. What is the frequency? Well, we know the angular frequency. The question is, what is the frequency? What is the relationship between frequency and angular frequency?
We didn't really get a formula for that.
We didn't get a formula, but we kind of know the relationship because,
However,
you said that, so frequency would be how,
how often the cycle happens.
yeah, and then,
Angular frequency, vaguely, is how often a circular angle happens that is associated with the frequency.
All right, let's do a different approach. Instead of finding frequency, let's find period first.
okay,
If I gave the equation y equals cosine of t, what would be the period? How long does it take to repeat itself?
1.
Not 1.
2 pi?
Hold on, it's 2.
I don't know if it's pi
Cosine.
or 2 pi.
It's 2 pi. Cosine of 0 is equal to the cosine of 2 pi. If I plotted it out, my cosine curve, it would look like this, where this is time, this is y, and that would be 2 pi. So 2 pi seconds, it was, you'd be back where you started.
Wait, who says it's 0?
It's
Are you
just-
starting at, like, the time is 0?
Yes,
Oh,
0, 2 pi.
okay.
If I did y equals cosine of 2t, what does that do to the graph?
Shortens the period.
It crunches it this way. So it's, in terms of the wheel, if the wheel is now spinning twice as fast, so it takes half the time to go around. So that plot, assuming that's 2 pi right there, that's pi, would look like that. If I did 3t, and now it's going 3 times faster, so the period gets cut by a third. In essence, the period, if I have cosine of omega t, the period is just 2 pi divided by omega. Whatever the coefficient of t is, 2 pi divided by that gives you the period. So the period is 2 pi divided by 1.83. So I guess technically that's radians, and this is radians per second. It's radians per cycle. Two pi divided by 1.83.
0.43.
Units?
It's just cycles per second. But you're dividing by radians on both sides.
Yeah, radians go away.
Yeah, so cycle over second. Oh wait,
Seconds
it's
over cycle.
Dividing by a fraction, say it's multiplied by the reciprocal, so you multiply by the reciprocal, so you have seconds on top. Seconds per cycle, or just seconds. All right, so that's the period. So now how do I find the frequency?
The inverse of that.
Yeah, so 1 over 3.43. Units,
Cycle over seconds.
otherwise known as,
Hertz.
and hertz is a capital H, lowercase c.
Dr. Fox is 0.29.
Thank you.
So if we didn't find the period first, how would you have wanted us to find the frequency for that?
All right, so we have that, so looking at those relationships that we just laid out, I know that the period is 2 pi over the angular frequency,
Right,
which is 1 over the frequency.
right.
Cross multiply here, I get 2 pi times the frequency is equal to omega.
Got it.
As a matter of fact, your book, when it does the generic equation for the oscillation, it does not do cosine of omega t, it does cosine of 2 pi f t. So it doesn't, it skips that and just uses that instead.
Can I ask a question?
Sure.
If omega t in the cosine function is radians per second times seconds, isn't that just radians?
Yes. And then you take this cosine of, it's an angle. So you
So,
take the cosine of.
it's theta.